So believe it or not, you are now ready to understand triple integrals. Okay? And why are you ready? Because it's simply extending everything analogously to how we extended from 1 dimension to 2 dimensions. We just add a third dimension. So it's very simple. So a triple integral, which is written as 3 integral signs. So this is an integral over 3 variables, x, y, and z. So remember, in 1 dimensions, we had to define an interval. In 2 dimensions, we had to define an area in the xy plane. So in 3 dimensions, we have to define a volume in x, y, z. So this volume, we call it v, and we just write v here near the integral signs. So an integral of a function that depends of x, y, and z with respect to v, this is the differential of volume. This can be defined as a Riemann sum. And we are going to do exactly what we did. It's the limit when delta x goes to 0, when delta y goes to 0, and when delta z goes to 0 of a triple sum with indices y, which are changing the x variable, j, which are changing the y variable, and k, which is an index changing the z variable, of our function evaluated at xi, yj, zk times delta x times delta y times delta z. And these 3 deltas together, of course, are just delta of the volume. Okay? So we are dividing a 3-dimensional volume we are dividing it into cubes. Okay? So that's why we have 3 sums, one inside of the other. And for each cube, we evaluate the function at its center. So the function at xi, yj, zk. And then we multiply the volume of the cube, which is dv, delta v, times the function, and we add up through all of the cubes. And that is our triple integral, in the limit when the cubes are made infinitely small. Okay? And similarly to Fubini's theorem in 2 dimensions, you can also do it in 3 dimensions. Okay? So a triple integral on a volume v of f of x, y, and z dv can be written as an integral inside an integral inside an integral. So let me do that. Parenthesis, integral, parenthesis, integral of our function. And then we have to do the integral first, let's say, along x, then along y, and then along z. And similarly to 2 dimensions, we can change the relative order of x, y, z between them. It doesn't matter, okay? But what we need to be careful is that if we first integrate along x, then the limits must correspond to the limits along x. So x from a to b. Let me draw x, y, z. So x from a to b. Then y from c to d. And then z is changing from e to f. And this defines a cuboidal region, right? Now things get tricky to draw. So I don't want to get lost in just the drawings. But this is defining a cuboidal region. So let me draw the cut plane at E and at F. So this area here in the XY plane, I need to copy it in the planes Z equals C and Z equals F. And this is creating a cube. This is a horrible drawing. Sorry for this. Let me clean it up. Okay, much better now. So this is a cuboidal region, yeah, which is defined by x going between A and B. So those are the limits in the x direction. Y is going between C and D, which are the limits in the y direction. And Z is going between E and F, which are the limits in the F direction. Okay, and this creates this cuboid shape. So that is how you calculate triple integrals. And you know exactly how to calculate them. You first do the inner integral, which will get rid of the variable x. So the result will be a function of y and z only. Then you do the integral along y, assuming that z is constant. And this result will remove the dependence on y, so the result will be a function of z only, and therefore you are ready to do the final integral along z, which will get rid of the z dependence, so that the final result will be the volume integral, which will be a constant that doesn't depend on x, y, or z. Okay?